Good morning to one and all. Welcome you all to this program. Make It Academy is a platform focuses on students' professional and technical skills, which helps them to enhance the knowledge in all the aspects. We are in the constant arrangement of exclusive webinar guest speaker session along with various technical and non-technical competition. The guest speaker session will be handled by our speaker residing throughout the world with various destinations. Today, our Make It Academy presenting you the exclusive international webinar based on in-memory computing and its applications. Welcome you all. And a very happy and warm welcome to our resource person, Sir Dr. Sridhar Chak, researcher, NCTU, Taiwan. Welcome you, sir. We are very pleasure to hand over the program to you. Thank you for your presence. Let me hand over the session to him. Thank you.
Thank you, ma'am, and very good morning, all. And today I'm going to talk about in-memory computing and its applications. And as we all knows that our next generation of computing will be completely based on high performance-oriented based computing, where like the CPUs, traditional CPUs will be replaced with human brain kind of computation. So and here I'm going to give you some basic insight about my previous expertise. And I lived in a country called Taiwan, and where I did my PhD from National Chiao Tung University. And I worked with NAR labs and NFCs and all these semiconductor fabs I worked with, and we fabricated resistor synapse kind of devices, which is typically a memristor, which is composed of metal, insulated metal kind of structure. And we worked in a clean room fab where we built from bottom end and front end and back end process of on silicon wafers. And let me give you all a brief introduction about what would be the focus of today's talk. And first case is like traditional one human computation architecture, where like CPUs is connected with a memory unit, which is typically your hard disk in your CPU, which is found in your CPU box, and followed by a CPU, which is a processing unit, which are connected by a bus interface, which is technically composed of 64-bit or 32-bit line, which is used to interconnect your processor with memory. And your processor job is to compute all these datas, and memory is to store all these datas. This is what traditional computing, which is one human kind of architecture. And what we are going to look at is like completely a different kind. It has like every nodes of this kind of sort of devices has a separate processing unit, which is typically a neuron, and followed by a synapse, which acts as a memory unit. And it's just like typically like a human brain. So as we all know that our human brains are like composed of neurons and synapse. It's like three-dimensionally integrated networks. So these networks, what it do is like it collects the information from the synapse, which is like a storage element, and processed through neurons. And it's kind of an electric pulse. It's kind of an electric spike kind of plasticity, spike kind of response, which happens when one neuron connects with another neuron. So we call it as a spike dependent plasticity, which is like a synaptic plasticity of our human brain. So we try to mimic our human brain's cognitive activity using our semiconductor based devices. So here we typically use a neuron circuit, which could be a CMOS based neurons, or like op-amp based neurons. And we'll be also using synapse, which could be any form of traditional memories, or even a resistor switching memories could be a better candidate, or even MTJ and all form of emerging memories. Let me give you all a short introduction about resistive switching memories. Resistive switching memories is nothing but a metal followed by an insulator followed by a metal. It's kind of a sandwich stack. Like these two metal uh, uh, like try to when we apply potential across these two metal, what happened is like oxygen vacancy based filament bridging is happening, as a result of which like the whole capacitor conducts. It's a traditional form of capacitor with semiconductor background, like where we use metal oxide followed by two electrodes, which would be like traditionally called as a top electrode and bottom electrode. And let me give you all some insight about how how the architecture of a human brain and the possible simulation on a traditional one-human architecture has been carried out. First of all, like when we look at our human brain is like typically a parallel architecture kind. Like since all these neurons are like cross-connected, so the whole architecture of a human brain is like parallel architecture with 10 power 11 neurons, approximately around 10 billion neurons with 10 hertz of operating frequency, like operating. It's completely like an analog signal response. And on the other hand, these neurons are interconnected with 10 power 15 synapse, which is typically our processing unit, and which consumes 20 watt of power. So this shows like our human brain is like quite efficient with smaller clock and smaller power operating power, and simulation of a mouse cortex has been conducted by IBM's Blue Gene L. It's a kind of a supercomputer, which is like advanced kind of supercomputer, which follows a traditional one-human architecture. So where they try to build 18 to 10 power 4 neurons with these kind of complex supercomputers, and they are followed with 10 power 5 to 10 power 10 synapse with a larger power consumption of 40 kilowatt. So this shows like our human brain is like most efficient because it occupies less. It consumes like very less power and higher speed and defect tolerance. That means like and architecture is also like more or less like a parallel architecture, and tolerance to defect is like since the number of neurons and synapses are like huge in numbers, like probability of prediction in a neural network algorithm is like quite highly efficient, because when you have more number of neurons and more number of synapses, your computation efficiency will be gradually increasing. And this shows like human brain dependent computing, like typically neuromorphic computing seems to be an efficient candidate to be our next generation computation. Uh, then I'll be giving you all a quick insight about the emerging class of non-volatile memories. So, which could be traditionally used as a synapse. As I said earlier, uh, the memory unit followed by neurons. That's the whole structure, whole building block of neural network. And so here, firstly, we will look at the memory part, like which is like a synapse part of a neural network. So there are a few candidates like magnetoresistive memory effect, like which is like MTJ, magnetic tunnel junction kind of memristors, which is like followed by which works on the magnetic polarization variation, which leads to the switching on and off of these devices. And this can also be integrated with traditional MOS transistors, and this can also be a very uh, prominent candidate for a emergent class of memories. And on the other hand, we are also having a ferroelectric class of memories where the uh, ferroelectric polarization change leads to the change in the states of the device from zero state to one or one state to zero. So these ferroelectric materials are change their phases. uh, which is like somehow relatable to the phase change memory and electric effect. It's a combinational effect of these these two combinational effects. And on the other hand, like phase change memory effect, which is typically we'll be using a phase change material sandwiched between the top electrode and the bottom electrode, followed by an heating contact, which is like typically a metal contact to a phase change material. And for example, like all our optical devices are like mostly somehow relatable to phase change, because when we apply optical or laser source inside our storage material, like due to the application of laser source, there will be a change in the heat, and these heat um, typically change the phase of the material. And once the phase of the material changes, what happens is like the conductivity of the material changes drastically. So these kind of connectivity change actuates the like storage capability of the devices. So for example, for the case of phase change material, when we apply a larger temperature, reset is happening, which is like reprogramming or erasing of our memory. So when we apply smaller temperature pulses, like or some smaller electric field for this case, and for an optical case, we apply laser source. And when we apply a smaller electric field, we can write these devices. And this is another next generation class of membristors, where the bottom electrode and top electrode are sandwiched between like carbon nanotubes, and which is like spin coated carbon nanotubes. This is completely a mechanical effect. Like what happens is like when we apply potential across the top and bottom electrode of a sandwiched carbon nanotubes, what happens is like due to the applied potential, it's a kind of a mechanical effect happens in these devices. What happens is like these carbon nanotubes are tends to be like stretching and straining kind of behavior it exhibits. When we apply a potential, larger potential, these carbon nanotubes are like stretched, or like they compressed, and leads to the conduction of leads to the transformation of a resistant state or conduction of our memristor. When we apply a negative potential, what happens is like relaxation of these carbon nanotubes can be significantly achieved. And these two classes are like typically resistive switching memories, which are like which works on two different kind of mechanism, like electrochemical metallization effects, which is like a CB-RAM, and valence change memory effect, which is like a NOx RAM. So these two are like our prime focus of today's snaps. And electrochemical metallization effects, which is nothing but electrolysis. If you electroplating, for example, when you consider electroplating, we will have our anode and cathode uh, followed by a electrolyte solution. Our objective is to coat our one electrode with either AG or AU. Then what happens is like we apply the potential across these electrodes, and as a result of these potential changes, like AG ion tends to move towards the neighboring electrode and try to coat on the opposite polarity electrode. And as a result of which, what happened is like electrocoating is happening. So this phenomenon is similar to that kind. What happened is like instead of electrolyte, we have our insulator followed by two electrodes followed by AG and PT. So when we apply a positive potential across the AG, what happened is like the AG ions from the top electrode moves towards the bottom electrode. And what happened is like here you can see from the TU analysis image, these AG ions from the top electrode, you can see carefully like they try to form a bridge kind of structure. And this bridge is composed of AG ions. And AG, as we all know, that AG is purely conductive material, which is a metallic kind of material, and the ionized Ag is like highly conductive, and this is like separated by SiO2. So what happened is like due to the formation of this wire or a bridge kind of stuff formation leads to the conduction of these insulator. So once this conduction happens, there will be changes in the resistance state. Like your 10 device tends to be conductive. And similarly, when we apply a negative potential, these nanoscopic shaped filaments will be like ruptured. So when the rupture happens, there will be a minimal conduction or like increased resistance state. So when there is an increased resistance state, there will be a drop in the current or IV characteristics, and as a result of which, like we can switch it on and off these kind of devices. And why do we prefer RM? Like here, I'm going to share about Nature article from which is published by Samsung. It's a corporate research conducted by Samsung Electronics, and they did on PT, TAOX, and PT kind of structure, which is like PT is a metal and TAOX is a metal oxide, and PT will be a top electrode. So this is simple metal insulated metal structure, and what they did is like they applied potential across these devices, and these devices are tends to be like switching, and here you can see like 10 power minus 4, which is like higher current region, and here you can also see like 10 power, approximately 10 power minus 5, which would be like a lower current region or higher resistance region and lower resistance region. So these devices, they are like capable of working on a longer switching cycle, and they can program and reprogram. They can program and reprogram for 10 power 11 cycles, which is quite huge. So imagine you can use a pen drive for 10 power 11 cycles. That means like around 10 power 11 times you can store and restore, erase your data. So that kind of thing can be possible with RM. So this is also another property which makes us to choose RM as like a better candidate for these kind of storage section of our neuromorphic system. And here is a comparative study, comparative tabulation of various class of memories. And here you can see like NOR and NAND flash, which is like our traditional class of memories, which are dominating our current products, right from your solid state devices to most of our trend drives will be followed up with NOR NAND flash kind of structures, and followed by RAM. And here you can see like RAM tends to be operating at lower operating at higher speed operation, which is like 10 nanoseconds. So high speed operation, which is crucial for next generation computers, because if memory can operate at high speed, hence your processor can also be like can operate efficiently. So high speed can be possible with RAM, and read time also can be like miniatured so that you can access your data at a smaller number of time, and also like zero point 0.1 to 1 picojoule of write energy. So this is also another interesting thing which you need to look at it, because if you have a smaller energy consumption, you can save a lot of power in your devices. So once you tend to save a lot of power, your battery size can be like miniaturized. So you can use a small size battery to operate your device, and so those things are possible with these kind of emerging classes. And similarly, as I said, endurance of 10 power 11. So I'm sorry, this one is like not updated, but up to 10 power 11, it can give good endurance, and retention is also good, and stability is also somehow okay. And another most important thing is like SSD switching memories are like CMOS compatible class of memories, where you can use them with a traditional CMOS process. So, for example, RM doesn't need any complex stages because just need three-layered mask to complete the whole stack. But for the case of PCM or spin transfer top or FE-RAM or FE-FET or STOM RAM, all these takes uh, complex structure. They require a complex structure, and either you need to use a specific material, which would be like expensive for a commercial fab to be used, and those kind of complexities can be mitigated by resistive switching memories because it will offer you cheaper cost of fabrication. And here I'll be just showing you circuit diagram of a typical fire neuron and synapse structure. So here is our fire neuron structure, which is typically our processing unit, as I said. So here the functionality of this neurons is to generate a spice signal, and here this group from US, they integrated these neurons with resistive switching random access memory array, simply RAM array. Like RAM generally fabricated in a crossbar array. Like this is one cell. This, if this is a bottom electrode, this is like top electrode. So followed by our insulator. So bottom electrode and top electrode came in contact. The insulator at this point. So this acts as a cell. This acts as another cell. So it's just like a matrix. You can say like each and every cells are interconnected with bottom electrode and top electrode. Similar to a matrix, you can select a row and column to choose your cell, desired cell. So that kind of structure has been used here, and they shown the back end of the wafer of the PCB board, like where the back end of the bottom electrode of the RAM is connected, fused with these neurons, and here you can see the metal lines from the bottom electrode are like they may be wired bonded, and they are connected to the respective neuron circuits. And here this fire neurons are composed of like amplifiers followed by a simple comparator circuits and a phase controls followed by a spike generator. So what happens is like these spike generator generates the spike continuously, and as a result of charging and discharging effect of Cn capacitance, your spike time dependent elasticity can be mimicked by these fire neurons. So these neurons tends to produce the or fire the neural activity, and all these fired neuron signals will be stored inside a RM, so as I said earlier. And so I just try to be like explain these complex topics in as short as possible, because it might take a longer time if we explain it clearly. And, next topic will be like applications of uh, uh, these neuromorphic circuits, how they used globally. Like one Korean research group, South Korean research group, have conducted successfully recognized our human brain's EEG signal. Like what they did is like they asked their subject to think about a character A or character I or character U, and they implanted these EEG electrodes on top of their scalp, and they tried to analyze the EEG signal. So when they think about A, the EEG signal shows some minor variation, and when they think about I, the EEG signal shows a minor variation in their potential, and when they think about U, similarly they exhibit change in their activity, like change in their peak. So this shows like depending upon the characters, yeah, your characters change, your EEG signal differs in your human brain. So that's they analyzed and tried to dump these response inside a neural network, which is composed of switching random access memory, which is a crossbarred memristor array. So here is their circuit, and followed by an FPGA, uh, which, like, as we all know that FPGA is like a programmable array, and they programmed the neuron part in the FPGA and try to instantiate or initiate the uh, try to store these data in the memristor array, and memristors uh, stores the part of these data uh, the synapse part, and the neurons which holds the prime data like decision making thing can be done by the neurons, and when we when they connect these electrodes inside the human brain, and they try to recognize, let the human brain think about A, and they train this neural network to, like, say say it in a voice like A. He thinks about A, like just like visualizing a human dream. Like here, they try to visualize a character from our human brain. Like, they try to identify what are you thinking as a character. But soon, maybe like we could develop much complex technologies which could allow us to think more, like which could allow us to think about a sentence or even visualize your human dream. So that kind of possibilities are there. Like you can record your human dream and watch it tomorrow or day after tomorrow from your storage stored memories. So these kind of possibilities are still there with memristor class of neural networks, and this is like an initial stage where they try to recognize a character. Maybe in future we could able to do more. Yeah, and as well as the face classification, which is like first option which comes into our mind when we think about AI or neural network, because our Facebook and all the social medias are currently focused on face classification or word they try to build on our complex servers. So those kind of using a complex servers, large scale computers can be mitigated by, can be avoided by using these kind of memristor classed neural networks which are otherwise uh, considerably smaller space. And here, group from Stanford, they try to work it out using a one transistor, one resistor array, which is like a traditional form of array, resistive switching array. Uh, and these synapse stores the uh, some of the pictorial data of this person's face, and what they try to do is like they dump part of this data inside these synapse and try to recognize the identify the face of a human brain by using a camera to analyze, like find is it person one, person two, or person three. As I said earlier, here they used aluminum 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 oxide doped with alumina, HLALOX, and followed by TOX. And here TIN act as a bottom and top electrode. And this is the switching of our resistive switching memories. Here we can find like the X and Y plot is followed by voltage, followed by current, and here when we apply the voltage, when we apply the potential, you can find the current is increasing. So after a certain point, the current is decreasing. So it's like a double sweep, we can say technically. What happened is like uh, this resistance, if we calculate, current is like inversely proportional to resistance, as we all know that. So this difference, we can say like considerably larger difference in resistance state. So that's why we traditionally call it as like higher resistance, because um, lower current which we can say it has a higher resistance, and here we have a higher current, which is like inversely proportional, so larger resistance is possible. So by this, like we can turn it on, and during reset we can turn it off these devices. And here they try to uh, actuate these synapses by applying electrical pulses. And here also we can find like change in the conductivity of these devices. Just like this case, like here, conductivity change happens from here to here, right? So similarly, there is a connectivity change happens. So this is like a potentiation of our human potentiation of our human brain, and this is like a depression of our human. So generally, like our human neural networks have a potentiation when there is an increase in the cognitive activity, depression when there is a decrement in the cognitive activity happens, and these neural networks are also uh, providing lots of opportunity in near future, like from our medical electronics perspective, we can say like even we can implant implantable electronics in our human brain, just like Tesla's neural link, like where they try to implant brain implant and analyze the cognitive activity of our human brain. So similar to that, we can implant implantable electronics on human neurons and try to control any kind of electronic devices uh, with just thinking itself. So those things, those possibilities can also be possible. And for the case of medical electronics, we can connect these kind of artificial neural networks implanted on our heart, and we can train this neural network in such a way that when there is a blood pressure change disorder, you need to alert the wearable electronics like that. So those kind of programmability can also be feasible. So it will monitor real life, like your all the data can be monitored real life time, and they followed by a antenna like microstrip antenna, like which is used to connect with our wearable electronics, and they fed the data from our heart to the wearable electronics. So those kind of possibilities are also like quite open, and maybe in future our medical electronics will be completely different. And what are the other application of neural network? Recently, many people are working towards mitosis cells detection in blood cancer cell. Uh, they try to like if they find a mitosis cell early in an early stage, so which is quite good to save many lives, who are like many people who are suffering from breast cancers, like without uh, letting them into the complex situation, we can save their lives. And so what they do is like try to analyze the whole OEM picture of these cells and fed into the neural networks. And what these artificial neural networks do is like they are trying to know the shape of mitosis cell. And once they found the structure of a mitosis cell, since these AIs are like highly trained, and which is like quite advanced than a human eye. Like human eye takes longer time to analyze and recognize. Sometimes human error also possible. So those kind of possibilities can be nullified by these ANMs, and we can use it in an efficient manner. And in another application which is in real time, like face recognition, and which is found globally, like as at the moment Facebook and all the social media platforms are like try to um, do the face recognition algorithm, much better face recognition algorithm to efficiently map the face of a human and then try to recognize it. And have you ever seen like in Facebook, like we can automatically it will suggest you the tagging of a person with respect to the uh, face of a person. It will suggest you the which person it is. Like those kind of suggestion can also be possible with AI. But at the moment, like people are training it with the supercomputers. They are doing it with supercomputers, but sooner or later, neuromorphic computers can replace them. And similarly, like portfolio management and target recognition. So lots of potential are there in this domain. Huge market space will be depending on maybe in near future, because our future will be like data centric, because at the moment itself we have a huge hunger for data, and compared to the 10 years back, 10 years back we will be wondering even 50 MB is like quite expensive, but nowadays we see like 1 TB and 2 TB are the, like expensive memory classes, memory terminologies we say. Like, so maybe next generation data centric uh, computation can be efficiently done by these neural networks and neural networks based complex systems. And still like uh, qubits takes maybe years or maybe like few decades to make it commercialized, because some of the qubits computers by IBM and other top notch researchers are like not, they haven't converted into handheld devices because they require larger space. So still like your network has a much better potential. Even credit rating, like typically you might have heard about in China, people do credit rating depends upon the activity of these people. So what they will do is like these AIs will automatically see the automatically analyze the human face with cameras and store record these data and rate it in their rating system. Like if someone steals something or if someone spit on public, so all these data will be recorded by AIs and they will report it to the rating system, and the citizens' credit rating will decrease by time. So for those kind of applications also, actually in China they are using it in real time, and similarly like voice recognition and face recognition kind of application is also quite open, and financial forecasting and intelligent searching kind of stuffs also be like intelligent searching in a sense like um, some cases like people try to analyze the drugs uh, effectiveness, like drug in the sense like medicine drugs. Uh, if, for example, people invented a new medicine for COVID or something, some diseases, and what they do is like they they input all these data into the neural network and ask the neural network to simulate the effectiveness of these drugs. So such kind of searching is also be possible, and fraud detection can also be possible with ANN. And summary, like artificial snaps and their applications are like ever increasing. Maybe in future we can find a lot of medical electronics to be the next focus. We can see a lot of implantable electronics inside a human body, followed up with a neural network. So that kind of uh, possibilities are like quite open, and even like EEG signal recognition with that, even we can visualize a human brain. Those kind of possibilities are also quite open. Even mitosis cell detection in breast cancers, so we can detect early stage breast cancer, breast cancers. So that can also be possible. So this will move further with our artificial intelligence, like hardware dependent on artificial intelligence technology will be soon possible. Like you don't need a complex server to construct the AI. So you may need a small kit to do your AI-based technology. Maybe our future will be based on this. And, uh, and also, I would like to discuss about the opportunities in Taiwan. Like uh, Taiwan gives you a wide opportunity. Uh, Here is the location of Taiwan. It's like nearby China and Japan, and Taiwan is like a safest country in terms of COVID-19. Like it ranked 7 and still reported they are reporting zero COVID cases, and they're fighting pretty well COVID-19, and they are like one of the leading countries with much better medical safety. And if you are the students who is searching for the next stage of your career, who wants to do your higher studies in much better university, you can try give a give a try with Taiwan, do PhD study and masters or bachelors. And masters and PhDs, you may not need submit your GATE or GRE, and that's a quite interesting thing about this nation. And Taiwan is like a simply the hub of the world. Like so, if you're working on semiconductors or like maybe like VLSI circuits or computer science, these kind of fields, you can get much better opportunity. And these are the top 5 universities of Taiwan, so which you can give a try. And I guess you've got much better opportunity, much better success rate to try early. And Academia Sinica offers lots of efficient scholarship, like fellowship of around 60 to 70,000. They will provide you for doing PhD, so that's quite good for a PhD candidate. And similarly, National Chow Tong University, just like a well-recognized university in Taiwan for electronics. So in this university, I did my PhD, and National Tsinghua for chemistry and nuclear physics, and even they are trying to cope up with electronics domain as well. And NTU and NTUST, these are like Taipei-based universities, and they are also like doing good, pretty good. So you can try on these uh, universities as well. And thanking you for listening. And this is a picture of our research group in Taiwan. And I hope you understand this presentation. If you're having any questions, please feel free to ask me. So Mr. Ravi Kumar asked me a question on which tool I can use for memory computing. So I felt like there are lots of uh, tools, open source tools available. You can refer NanoHub. They have so many open tools, and I need to know like what kind of memory computing you're focused on, like either neuromorphic computing you're focusing on, or you try to simulate a neural network. If your focus is on simulating a neural network, then I feel like you can use Python along with TensorFlow uh, software, which is like typically used to simulate a Python coding. So in TensorFlow, you can build a much better neural network. And you want to start up on a simple neural network, you can go with MATLAB or other platforms to build your neural network. Please feel free to ask me if there is any questions. How can we extract features from speech imagination? How can we extract features from speech imagination? I mean, like uh, speech imagination in the sense like we want to extract a speech into a digitalized code means like we can use MATLAB, which is like a very good software. You can convert a speech or audio signal into a digitalized form, and then after converting into like digitalized form, you can use these digitalized form to use it in your neural network. That can also be possible. JHM, yeah. Like memristors are like general term for using for representing certain class, and RRAM is like one among the classes of memristors. So it's quite like generally we can also use memristor as a general term and RRAM as a specific term. Say memristors we can say either RRAM, PCM, or other class of memories we can also say as memristors, but RRAM is for specific devices. Oh, nice, Mr. Ravi Kumar. Good to hear, and I hope you will get some good things. Yeah, thank you, Mr. Balakumar. Yeah, thank you, Nita Raman. Sir, can we use it for high-powered application? Uh, Actually, high power means like we need to tune these memristors on a. We need to design everything high power range. Means like your memristors should be also in a high power range, or we can simply like reduce the voltage and current level of. We can compress the voltage level, we can step down their voltage and current depending upon our operating power. So by doing this, we can use it on a high power application. So this is also possible, sir. But we can't operate a neural network on a high power because if you want to operate a neural network on a high power, neural network based on synapse, residual synapse on a high power, we need to design a whole synapse on a high power. Hello, Chunki Pradhan. Yes, it's possible, but by analyzing the image, like simply like feeding a neural network with the data of mitosis uh, cell structure, like we fed the data of a mitosis structure, uh, and these data are stored inside our neural network. And what happens once we train our neural network will be like uh, using these data uh, and try to spot the cancerous metastasis, uh, so which are like highly uh, dangerous for cancer patients. So thank you, Nirmala. Can we use any circuit simulators for simulating neuromorphic computing systems? Yes, we can use circuit simulators, but the complex you can make a simple neural network which might be composed of smaller number of circuit elements. You can try to simulate can try to simulate an efficient synapse. You can try to develop a much better synapse for your circuits. So those things also can be possible with uh, circuit simulators, uh, and but you can't completely simulate a whole system with circuit simulator. The problem is that our neural networks are like interconnected with so many neurons, so it's difficult to exhibit in the form of circuits and complex structure. But we can make simple neurons and circuits with a simple structure, which is composed on 10 cells, right, which might be composed of 10 uh, neurons and synapses. Like such a simple structure can be possible. Thank you, ma'am Revati Raja. Thank you, sir Ravi Kumar. And if you have further more questions, please keep me taking. Yeah. Oh, yeah. Thank you, everyone, and yeah, it's good to interact with you all. And hope this session is quite informative.
Thank you, sir.
Yes, ma'am. Thank you very much for giving
Yeah.
me this opportunity. And I would like to take this moment to thank Professor Kiran Kumar, who invited me to have this session. So I'm thanking you for giving me an opportunity to interact with people. Yeah. Yes.
So much, sir. A special thank to Dr. Sridhar Chandrasekharan, sir, for sharing such a wonderful presentation about in-memory computing and its application. Really, it is wonderful and very useful for us. Thank you, sir. Make It Academy feel grateful to thank you all. We are also thankful to our valuable participants. Thank you so much. Participants will receive your e-certificate through mail. Stay tuned and keep supporting Make It Academy. And we have planned more useful webinars for upcoming days. Please visit www.makeitacademy.com. Thank you, guys.